Day 465 of doing a LeetCode problem. All right, y'all, we're back again. Another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 2438, range product queries of powers. The difficulty level is medium, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, comment, subscribe, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. Given a positive integer n, there exists a zero-index array called powers composed of the minimum number of powers of 2 that sum to n. The array is sorted in non-decreasing order and there is only one way to form the array. You are also given a zero-index 2D integer array queries where queries of I is equal to left of I, right of I. Each queries of I represents a query where you have to find the product of all powers of j, with left of I being less than or equal to j and j less than or equal to right of I. Return an array answers equal in length to the queries where queries of I is the answer to the ith query. Since the answer to the ith query may be too large, each answer of I should be returned in modulo 10 to the 9th power plus 7. All right, y'all, so that may seem a little bit confusing at first, so let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. So in example 1, we have our input n equals 15, queries equals a 2D array of integers 0, 1, 2, 2, 0, and 3. Output is 2, 6, 4. Explanation says for n equals 15 powers, the powers is the array of integers 1, 2, 4, and 8. So let's take a break right here and break down how they got this powers array from n, right? It says right here, there exists a zero-index array called powers composed of the minimum numbers of 2 that sum up to n. So as you can see, all of these numbers right here, if we add them all together, they're all the minimum powers of 2, and they all add up to n. When we add all of these elements together, we get 15, and n is 15. So let's break down how they got these elements. Now, first, I'm gonna give you two examples. First, I'm gonna give you an example that's not on here, and then we're gonna go through this example. First, we're gonna do an example of where n equals 10, just so I feel like that'll make it's easier to understand, because I'll tell you why as we get into it. So say n equals 10, right? So 10 in binary is equal to 1010, 1010. So to get the powers right for n, what we do is going from right to left, we're going to do 2 to the power of whatever index, but it's going from right to left, so index for lack of better terms, but this would be 0, this would be 1, this would be 2, and this would be 3. So wherever we see a 1, we're going to do 2 to that power, right? So give you an example. This is 0, but we see this is index 0, but it's a 0 right here, so we can ignore it because it's a 0. We're only worried about where we see the 1s. So boom, we come over here to 1, right, or index 1 for lack of a better term. So we do 2 to the 1 is going to equal 2. Boom. Then we keep going. We're going from right to left. This would be index 2, right? It's a 0 right here, so we can ignore it. Boom. Then we come right here. It's another 1. So since it's another 1, that means would be at 3, index 3, if this is 0, 1, 2. So this 1 right here would be at 3. So we're going to go 2 to the third. So 2 to the third, that's going to equal 8. Boom. So as you can see, this 2 and 8 will be our power array. Boom. And as you can see, when we add 2 and 8 together, that equals 10 just like it's supposed to. And that's how we got the elements 2 and 8. So now we're going to go through 15 just to make it make sense, because we're going to go through the example where n equals 15 just because that's what the example is, and I wanted to make sense. I chose this one because it had some zeros, so hopefully that will make it a little easier to understand, because 15 is just all ones, and that may have confused some people. So let's go when n equals 15. 15 and binary is 1111. Boom. So now we do the same thing. So we have, this would be 0. So we do 2 to the 0. It's a 1 here, right? Before it was a 0 here, so we could ignore it. Now it's a 1 here, so we can't ignore it. So we do 2 to the 0. That's going to equal 1. Boom. Then we come right here to index 1. That's a 1. So now we're doing 2 to the 1, right? Because every time we see a 1, then we're going to do 2 to the power of that index, for lack of a better term. I keep saying index just so hopefully y'all can understand what I mean. From right to left, though, and there's no array. So this would be 1, 0, 1, 2. So now we're at 2. So then it's a 1 at 2, right? So since it's a 1 at 2, we don't ignore it. So we do 2 to the 2. That's going to equal 4. Boom. Then we do it again all the way for the last one. It's a 1 right here. Remember, if it's a 0, we can skip it. We can ignore it. But here it's all 1, so we're not ignoring anything. So now we're at index 3, and that's a 1 as well. So we go to the third because we're at index 3, and that's going to give us 8. Boom. So that's how we got these integers right here. As you can see, we have 1, 2, 4, and 8, right? That's what we have right here. Same thing they got over here. Boom. So that's how we get the powers. Now it says it can be shown that powers cannot be a smaller size. The answer to the first query is powers of 0 times power of 1, which is 1 times 2. So this tells us which index we are going to find, multiply, or excuse me, we're going to find these. This tells us what powers we are going to multiply. So we're going to multiply powers or indexes 0 and 1 in the powers array, right? So we have this powers array. We come to indexes 0 and 1, which is a 1 and 2. So we multiply powers of 0 times power of 1 equals 1 times 2, which equals 2. So we put 2 and append 2 into the output array. Then we come down and do it again for the second query. The second query is 2 and 2. So answer to the second query, we don't have to multiply 2 by itself. We could just do powers of 2, which equals 4, right? So second index becomes 0, 1. So this is the second index. It's 4. We don't have to multiply it by itself. We could just add the 4. So we append the 4 to the output array as well. Then we come down to answer 3, or our third query. Our third query is 0 and 3. So 0 and 3, this means we're doing every index from 0 all the way up until 3, right? So we do powers of 1, or excuse me, we do powers of 0 because that's where we start, times powers of 1, times powers of 2, all the way up to times powers of 3, because once again, the query is 0 and 3. So that is going to become 1 times 2 times 4 times 8. That's going to equal 64. So we append that 64 into our output array as well. This is our output. These are our 3 queries. As you can see, the output is the same in length as the queries, like it should be. And yeah, so see, it says right here, return an array answers equal in length to query. So that's how it is. There's 3 elements in the output. It's 3 arrays in the query, in the 2D array query. So that's how we got this output. So now let's take a look at example 2. In example 2, it's a little simpler. We have n equals 2, queries equals 0, 0. So the output would be 2. Output is 2. It says for n equals 2, the powers array, we're only going to have, it's only going to be a 2 in there. Then the answer is to the only query is powers of 0, which is equal to 2. So the answer module 10 to the 9th power plus 7 is the same. So 2 is returned. So I hope that makes sense to y'all. And now that we understand the question, let's get into the fun part, the actual solution. Y'all, solution is not that difficult. So let's get into it. Now, the first thing we want to do, it says the answer should be returned module 10 to the 9th power plus 7. So we are going to handle that first. We're just going to say let mod equal is going to be 1 underscore 0 0 0, another underscore 0 0 0, another underscore 007, just like that. Boom. Now we need to extract the powers of 2 from the binary representation of n, like we did in the examples, and powers is going to store the individual 2 to the bit values corresponding to set bits in n. So we're going to create that powers array by saying var powers colon is going to be an array of integers. We're going to initialize it with an empty array just like that. Boom. Now we're going to say for bit n 0 dot dot less than 31, we're going to open up the brackets. Now this is enough to handle up to n, or handle n up to around 1 billion or 31 bits, right? So we're going to say, we're going to check if the bit at the position bit is set in n. So we're going to say if, open up the parentheses, n less than left shift bit, and one and sign, or binary and 1 equals 1, we're going to, or bitwise and, sorry, 1, we're going to say if it is set, we're going to append 2 to the bit to the array. So we're going to say powers dot append, open up the parentheses, 1 less than bit. Boom. Now step 2, we're going to pre-compute the prefix products module mod, and this is going to allow big O1 range product queries with modular inverses. So we can come underneath this for loop, we can say var prefix prod, set that equal to an array of integers, open up the parentheses is going to be repeating colon 1 comma count colon powers dot count. Boom. Come underneath this, we're going to say prefix prod square bracket 0. We're going to set that equal to powers, sorry, I should say powers square bracket 0. Come outside of that, we're going to say mod, just like that. And the first element is just the first power. Then we come underneath this, we're going to say for I in 1 dot dot less than powers dot count. We're going to open up the bracket and multiply previous prefix product by the current power. Take the modulo to keep numbers small. So we're going to say prefix prod square bracket I. We're going to set that equal to, open up the parentheses, prefix prod square bracket I minus 1. Come outside of that, we're going to say times powers square bracket I. Come outside of that, we're going to say mod. Boom. Come underneath this, and we are going to say, or now we need to process each query. So we're going to say var result. We're going to set that equal into an array of integers, put the parentheses. Then we're going to say for Q in queries. We're going to open up the brackets, and we're going to say let L equal Q square bracket 0. Then we're going to come outside that, say R equals Q square bracket 1. Boom. Then we're going to come right here underneath this, we're going to say if L equals 0, we're going to open up the brackets. And if the range starts at index 0, the result is just the prefix prod R. So we're going to say result dot append, open up the parentheses, prefix prod square bracket R. Come outside the square bracket, still inside the parentheses, we're going to say mod. Boom. Then we could come right here and we're going to say else. We're going to open up the bracket. So otherwise, we're going to divide prefix prod of R by prefix prod of L minus 1 under modulo division. and division under modulo is done by multiplying with modular inverse. So we're gonna come right here. Or first we need to create a helper function. So first we're gonna create a helper function. We're gonna come outside of this function. So we're gonna come right here, and we are gonna say, so this is going to compute the base to the exponent mod efficiently using our binary exponential. So exponentiation, sorry. So we're gonna say private func mod pal, open up the parentheses, we're gonna say underscore base colon, that's gonna be integer. Then we're gonna say comma underscore exp colon, that's gonna be an integer, comma underscore mod colon, that's gonna be an integer as well. Then it's going to return an integer. We're gonna open up the brackets. So first we're gonna say var result. We're gonna set that equal to 1. That's gonna accumulate the final answer. Declare another variable called base. We're gonna set that equal to base mod, and that's gonna keep the base within the mod. Then we need the exponent to be processed, so we're gonna say var exp. We're gonna set that equal to exp. Then we're gonna come underneath that, we're gonna say while exp is greater than 0, we're gonna open up the brackets. If the current bit in exponent is set, we're gonna multiply the result by the base. So we're gonna say if exp bitwise and 1 is equal to 1, then we're gonna open up the bracket, and we're gonna say result equals, open up the parentheses, result times base, come outside the parentheses, and we're gonna say mod. Boom. Now we're gonna square the base for the next bit modulo to prevent overflow. So we come underneath this if, and we are gonna say base equals, open up the parentheses, base times base, come outside of that, we're gonna say mod again. Now we're gonna move to the next bit of the exponent. So we could come underneath this, we're gonna say exp greater than 1. Then we could come underneath that and we could just say return result. Boom. So now we need to call this helper function. We're gonna call it over here, up here in the else. First, we're gonna say let numerator equal prefix prod of r, so square bracket r. Come underneath that, we're gonna say let denominator, so denominator inverse, or we're gonna just say inv for inverse. We're gonna set that equal to mod pal, the function we just created. We're gonna open up the parentheses, we're gonna pass in prefix prod square bracket L minus 1. Come outside the square bracket, we're gonna say comma mod minus 2 comma mod. Boom. Then so that's Fermat's little theorem right there. Then we're gonna come right here and we're gonna say result dot append, open up the parentheses, numerator times denominator in, come outside of that. Oh, sorry. So this should be in parentheses as well. Then we're going to come outside of, sorry, y'all, hold on. It should be parentheses. Boom. Then we're going to come outside of these parentheses, but still inside the other parentheses. And we're going to say mod. Boom, y'all. That should be all she wrote. Let's give it a run. Make sure it runs properly before we submit it. Okay, we have an error. Oh, how could I forget? We have to come right here and we have to say the return result. Boom. Now that should do it. Now let's run it. Now let's run and see if that works, y'all. Let's see. Time limit exceeded. I was about to say it's taking a little while. So let's see where we went wrong here. We got a time limit exceeded somehow. So somewhere we went wrong. See if we can figure out where that is. Oh, sorry. So it's right here, y'all. This should be uh left shift or equal. So it should be equal right here. So it should be exp greater than equal sign. So now let's run and see if that works. Sorry about that, y'all. And it's accepted. So let's go ahead and submit it. Make sure it's still accepted after we submit it. And look at that, y'all. 48 milliseconds beats 100% of users with Swift. That's what I'm talking about. That's what I like to see. So with that being said, y'all, make sure you get one more look at the code. This is the top part. This is the middle part. And this is the bottom right here, y'all. And with that being said, I hope y'all learned something today. And I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.